afternoon, everybody, and welcome to Zon Academy. Today, we have Milos Markovic, CDT, with us, and he is the director of CAD/CAM for Aurora Implantology, and I'm sorry, CAD/CAM and Implantology for Aurora Digital Technology Center up in New York. And he today is presenting on digital workflows. He's going to be taking us into a deep dive into an integrated solution from design to mill, featuring the XTCera mill. Milos has come up with a bunch of poll questions for us, so I'll be launching them throughout his presentation. So we'd love for this to be very interactive. So if you wouldn't mind, take a moment and just answer those questions for us, and we'll give Milos all the answers at the end of his presentation, along with Q&A. Q&A will be at the end as well, and you could just type in your questions at the bottom of your screen and at the Q&A section, and we'd be happy to answer any of the questions, like I said, at the end. So I welcome you all, and here's Milos. Milos, thank you so much for joining us today.
Thank you, Fran. My pleasure to be here. Hello, everyone. My name is Milos Markovic. I'm a CAD/CAM director at Aurora Digital Technology Center here in Wappingers Falls, New York. This presentation was interesting to work on because I took the opportunity to actually show everyone what sort of upgrades we've implemented at our facility and what was the philosophy behind driving the decision making when it came to those upgrades. And we're going to be talking a little bit about some of the economic factors and geopolitical factors and demographic factors and technological factors, innovation factors, all kind of in this medley driving innovation and just pushing people in different directions in dentistry today, and especially restorative dentistry. So Aurora Digital Technology Center is a manufacturing facility. You can call it a milling center, but we do a lot more than that. We are an overflow manufacturing facility, which means if you're a dental lab and you need assistance or help with a particular part of the manufacturing process, whether it's milling, staining and glazing, designing, or technical support, we can jump in any step of the way. So in that sense, we provide sort of like a wider range of support than your typical milling center. And that's what kind of gave us a competitive edge over the years. We are consistently upgrading our equipment and our facility with new software, new hardware, and we're also a location where a lot of manufacturers send products to be tested out. So we try to give them as objective feedback as possible on all these new technologies that are coming out. And so we put a lot of effort into understanding what are the drivers in today's restorative dentistry, and what is it that drives a technician to buy a new piece of equipment? Is it the right decision considering their current volume or their current setup or their current labor availability in their area? So we kind of try to put that all together and provide support for different labs when it comes to that. So over the years, we've upgraded and changed many different machines. These are some of the machines that we currently utilize, used to utilize, and we tried out basically almost every machine known to man in digital dentistry and dental manufacturing that exists today. Obviously, we started with the Roland ZWXs and the VHFs. We had the Haas machines, which actually were really good workforces for a very long time. Unfortunately, technology has changed, so we are able to compact a lot more quality and precision now in a much smaller package. And then we upgraded to Versa mills and different mills over the years and tested out so many different products. So today we graduated to sort of like a different solution, which we're going to be talking about today. I'm going to explain to you what drove our decision making. But before we proceed, I'd like to sort of like give a legacy of Roland DWX machine. This was a very important mill for our industry. It sort of like democratized and standardized the knowledge of milling in our industry. It brought awareness and gave a lot of small labs ability to sort of like dip their toes in manufacturing. And so it was a great startup mill for many labs. It was a good balance of quality and speed and allowed economical and technical growth for many labs. And also, it created sort of like a benchmark so that as the competitors were releasing their product, they were always looking towards Roland to see if they can at least match that or maybe supersede it when it comes to quality. Um, but the most important part of that story is that technicians who never had experience with milling learned the ins and outs of in-house production. They learned about path of insertions, tools, milling strategies, things that technicians were not aware of before. And so as everybody got access to it, we sort of raised the bar for quality and performance as the years were progressing. And so now labs became a lot more interested in better, faster, and even stronger future offerings that came onto the market. So it was a very important mill. It was a very similar effect to what Formlabs had on our 3D printing industry. Before in Formlabs, we only had this like high-end machines that were sort of like out of scope for a lot of labs. And then as Formlabs introduced their machines, sort of like allowed technicians to again introduce themselves, even smaller labs to introduce themselves to 3D printing, understand how the technology works, so that as their business grows, when they make their second decision on upgrades or future purposes, they're much more informed when it comes to making those decisions. Let's see. Sorry, I'm a little frozen here. There we go. And so demand for higher aesthetics and accuracy, which is what we experience today, drives innovation and automation and material science. So everything we do today is an effect of something. We don't just arbitrarily choose a new piece of technology, a new piece of CAD software, a new material that just came onto the market. Everything is driven by something that's going on in the market. And so it usually comes from the patient, but it also comes from the dentist, and it's a combination of various different factors. So let's go over some of those factors. So what are we seeing currently in the market that drives sort of like this change? So everybody wants better quality because this is driven by technology and patient expectation, mainly social media and data exchange, right? Back in the day, you maybe lived in a small town and you had access to only a few select dentists that only did things a certain way and only gave a certain level of quality and aesthetics. Now you have an opportunity to see how a million other people do things differently and a million other better outcomes maybe from what you're used to getting. So now that drives decision making and the patient's expectations are much higher. And then we have more in-house manufacturing. This has been a trend that kind of peaked around COVID because of obviously geopolitical limitations when everything got shut down. Everybody requested more in-house production in domestic production. And so this was mostly driven by geopolitical and economic factors. So now the trend is the world sort of wants to be prepared if a similar occurrence happens. Are we actually going to be ready for such an occurrence to do all the manufacturing at home? You see this trend with microchip manufacturing and a lot of heavy machine manufacturing either coming back to United States or moving to Canada or Mexico for more strategic positioning and ease of convenience in use. Now, because we wanted to bring everything home and start to do more in-house manufacturing, now we have a much higher demand for skilled labor. And so we run into a problem where the tech schools, the dental technician schools, haven't really generated a lot of graduates every year. And even if you look at a school that I come from, New York City College of Technology, even though they might generate 50 or 100 graduates that year, not everybody stays in the field. So actually the percentage of technicians who stay in the field is very limited, and it's simply not enough to satisfy what the market demands. And so there's a little bit of push and pull when it comes to education. And then now that we know that we have such limited availability of skilled labor, now we're forced to create automation. This is why you see the big push in artificial intelligence and automation and virtual intelligence, all these things that can sort of make everything easier and quicker and better. Simply because the labor availability is not there. There's a common misconception with AI that everybody just wants to replace everybody and robots do everything. It's actually a necessity that we have in the market that people don't see happening in the background, driving a lot of this innovation and wanting to create automation. So this is why I coined the term reliable automation. In order for us in the dental industry to be ready for these changes, we need reliable automation. And reliable automation needs two things: good hardware and good software. It is interesting that we're talking about dentistry. I'm going to keep going back and it's talking about hardware and software, but this is where we are today, and this is the reality of how our industry produces products. So these are very important factors. And so this brings us to HyperDent and XTCera. So these are the two solutions that we've integrated into our facility. HyperDent, we integrated a long time ago, whereas XTCera is the new addition that we introduced for a large scale and robust manufacturing. And we're going to go over to what made us kind of sort of take that route and move on to the previous machines that I mentioned in the slide earlier. And so we have HyperDent, which is a powerful CAM software, and you'll see how powerful actually really is. And I see that we have a poll question here. Do you feel a strong, robust, reliable mill is needed in order to grow your business and offerings? So I'll give you guys a few moments to answer the poll. Okay, perfect. So we have a powerful CAM software, which is HyperDent, and then we have XTCera, which is the robust milling architecture. And the reason I call it architecture is because of how it actually integrates with the nesting software, which is HyperDent, and sort of like the scope of possibilities and tools that this new mill gives us. So this is XTCera. So this is a XMill 500 Plus. It is a relatively small footprint machine. There's other models like the 580, which are large 12-disc changer machines, but this is sort of like our new standard that we implemented for all of our zirconia milling, all of our full arch milling. And right there, you can see it has a touch screen integrated. It is built like a tank. You can put it on your network to send jobs directly to it. You can do it via USB drive. And it is very simplistic in nature due to its modular nature, but also very robust. And we're going to go into more detail of what makes it very special. Our goal probably about a year ago was to replace all of our current milling with this mill. And we've slowly integrated more and more of these machines into our facility because we've realized that we can run these machines 24 hours a day and not skip a beat. And we're going to know why. So stability during milling. Everybody knows about that. Everybody has different theories about what drives stability over milling. You don't want your spindle to vibrate. You want your machine to have a certain weight to it, to be structurally sound or built with a certain framework that kind of allows for that to happen. What makes this a little bit different is that unlike most mills that are coming from the top, the spindle actually comes from the side. So it has a lower center of gravity versus a high center of gravity. So that means that by default, we have a lot more stability. It's a high precision double linear guide system versus what a lot of other mills use, which is a more singular rail system. So the way, and I took credit here from linearmotiontips.com, the way that it's explained is that machine tools require very high levels of travel accuracy and stiffness. And so when you put it on a single rail over two bearings, it gives you a lot of flexibility, but also it allows for a lot of movement over time. So this is a more of a double rail system that the spindle moves on, and it uses 4 bearings, which means it reduces the wear on the bearings over time. It also gives you a lot more stability, and then you can also spread those rails depending on what sort of stability you're trying to achieve. So this is what gives it that extra level of accuracy. We don't have to worry about the spindle shifting or moving. The next one was the power. A lot of mills are limited at 30, 35, 40,000 RPM. This mill goes up to 60,000 RPM because of strong 1.8 kilowatt motor. So now it allows a nesting software that makes a custom strategy for it. think outside the box and maybe implement different tools to take advantage of those 60,000 RPM, so we can actually cut down our hybrid milling from 5 hours or 4 hours down to maybe a 145 or 2 hours tops. So these are huge savings in terms of a saving on time, but also we get a lot more predictability knowing that we're dealing with a robust piece of equipment. So talking about robustness, we have a high-strength aviation aluminum alloy, and it weighs almost 440 pounds, so just under 434 pounds. Whereas most machines in this category, in this footprint, usually weigh about 150 to 200 pounds. So we also have that extra level of weight and stability. When I say it was built like a tank, it's not an overstatement. And so those are kind of like the basics. But what I was most interested in as somebody who likes to build computers, especially with the new cooling systems, I saw this, I looked at this machine and I saw this port in the back that said chiller on it. So I was confused for a little bit because I know that the only time I've seen water cooling implemented was in these high grade, high industrial grade machines with a giant footprint, because those machines generate a lot of heat and you have a cooler, whether it's in a form of an oil or an actual water coolant for radiators. So this machine utilizes something very similar. So it has a small chiller container, and the coolant goes inside the spindle and always keeps it at a steady temperature. It doesn't mean the spindle gets cold, but it means it keeps it at a steady temperature. And the reason that's important is with temperature variation, you have expansion and contraction. And so again, talk about spindle accuracy, stability, and consistency that just gives it another level of a peace of mind that we know that when we send a design there and it looks a certain way, that part is definitely going to get milled out. Those interproximal contours are going to get milled out. Those facial textures are going to all come through, and those angulated screw channels are all going to get picked up correctly. So it's a combination of all those things. So it was a very interesting thing to see, to implement something like that on a sort of like consumer grade mill, if you want to call it that. So here, I just want to show you, this is just an example of us milling a removable product. We're milling a flexible RPD denture, and I believe we have a polling question here, Fran, if you want to just put it up, of how many customers actually mill removable frameworks. Yeah, there it is. Are you currently milling removables at your office? I would like to know this because implementing removable restorations in digital dentistry has been kind of tricky. Emacs, zirconia, screw retains, that kind of like took off. We have a lot of good technologies that can do that, but people were still on the fence when it comes to removable because there's certain limitations, and the technology maybe wasn't quite there. Some of the milling blanks were expensive. The relining wasn't all that available. With 3D printing, we have so many different options. So it's kind of like a little messy right now. So we like to know how many of you are actually doing it. And I'm going to show you in this presentation what we actually do and how we implemented this mill to sort of benchmark it to see how good it really is, because it was my belief that if you can mill a certain flexible RPD designs with this mill, that you can basically mill anything on it, because these are some of the most challenging milling strategies that you're going to face. Here you can see how the spindle is side mounted. It's a C-clamp, obviously. So you can attack your facial, especially facial contour at a 90-degree radius to the spindle, 90-degree position, so the spindle can actually stay there and not having to deviate too much. Let me go here. Yeah. So in order for this mill to shine the way it does for us, obviously having good hardware is kind of useless if you don't have good software to accompany it, right? So you can buy a Ferrari, but if it's not running, that V12 engine is basically useless. So it needs to run very well. And with new technologies, the way engines work, it's all computers. So the HyperDent allows us to do several things. Its ability to adapt to changes in a fast developing environment. The material science produces so many different materials these days. The market is so competitive. There's new materials coming out monthly. And so when they come out, we sort of need to adjust the milling strategies on the fly for a lot of these materials whether they need us to slow the spindle speed or change the type of burr that particular material responds well to, so it doesn't gunk up the burr. So the software allows us to kind of change these things on the fly, and that we support if we don't know what we're doing, which it's a lot of times. We can easily call HyperDent, and they will be able to sort of like implement that strategy, put it in our system, and we're ready to go that same day. But they also allow you certain tools so that you can change those little things and test out a new material, see how it behaves, to see if you're actually ready for mass producing it. So those custom milling strategies and that sort of like out of scope thinking that it goes beyond what the manufacturer intended is really useful for us. It gives us a lot of flexibility to experiment. Even though a lot of people don't like to use that word, meaning, well, if you're experimenting and you're really putting out consistent product, if you really know what you're doing because it's all new, I like to call it that because we live in a market that a lot of experimentation is actually needed because of how quickly material science progresses and puts everything, all these products onto the market, sends them to us and you guys, and you're kind of stuck trying to figure out whether this is a product you can stand behind and offer to your dentist. And so on the computer side, it allows us easy server level blank database management. What that means is we have a server host for the HyperDent, and then we have all these clients. So if I have 4 or 5 people nesting, if one person pulls a blank, that blank gets locked in the library. So this person cannot mill the exact same case, mill a different case on the exact same blank. So that allows us, reduces the room for error. So it streamlines our production even more. Here, I would like to show you about the post processor. So when I talk to HyperDent and XTCera, because I really wanted to know how these systems integrate and how does a nesting software really know how to take advantage of the mill, right? There's so many mills that have different possibilities or parameters or limitations. So when the new mill comes out, HyperDent needs to know several things from the manufacturer. They need to know which tool should go in each pocket. Then they need to know things like the machine language, right? The understanding how you can send commands to the machine and communicate it. Different machines use different machine languages. They use different onboard pieces of software. Some use Linux, some use Windows, some use embedded Windows IoT versions. There's so many different versions. And then ultimately, they need to know the kinematics of the machine. How far can this angle be changed? How much of a deviation can you have with this particular tool? What sort of movement on the arm, if there is an arm, is limited? What is the degree of limitation for that particular movement? And so when you take all this data and crunch it together, they create this thing called the post processor. So the post processors is what basically HyperDent created for XTCera for their machines. And again, they've taken the XTCera's capabilities and sort of like taken them to the next level. So the way they did that is sort of like, unlock the possibilities of the mill. So on the left, you can see a standard set is what you usually get from most mills, consumer grade mills. You get a 2.5 millimeter, 1 millimeter, and a 0.6 millimeter burr. And so they introduced additional tools. HyperDent themselves developed different tools for this mill. And so that's a T-cutter for direct to multi-unit, which we're going to go over. A 21 millimeter long bull nose, also useful for direct to multi-unit, attacking the screw channel, angular screw channel from the occlusal side. But then my favorites are actually the 3 and the 4 millimeter burr. So remember earlier I mentioned that the mill can go up to 60,000 RPM. So if you have a 2.5 millimeter burr at 60,000 RPM, sure, that's better than most mills. But imagine if you had 60,000 RPM and a 4 millimeter burr, which means your bulk grinding, your initial grinding, which is taking away all that bulk material before you actually start fine-tuning the details, is done with a 3 and a 4 millimeter burr, which means you can remove a lot more material much more quickly, which even more reduces your milling time. So it's not just a combination of the specifications of the machine, is whether you provided additional tools to take advantage of that machine and its capabilities. So those are my really favorite tools. And especially when we do like high volume milling, like PMA, you know, you mill, there's a lot of dust, there's a lot of like chunks. Um, the burrs are designed in such a way to like sort of like push away that material so it never like clogs up the burr. So it's a really good solution. And this is sort of like what allowed us to kind of say, hey, not only do we have these mills with these capabilities, but now we have this tool set. So when we put it together, it works really well for us. And so also on top of that, HyperDent allows this thing called user-defined areas for HD milling. So we can go ahead and tell the software, okay, I'm really concerned about this area. I really want the milling strategy to focus on this particular area. As you know, in digital dentistry, we can produce some of the most beautiful designs, but if the machine is limited with limiting your design, you're back to square one, having to adjust so many interproximal contours just to get what you initially wanted from your initial CAD design. So usually ends up being a cursing match between the designer and the ceramist or whoever is working on finishing the product, having to redefine all those fine details that you should have gotten out of the mill in the first place. So I like that feature because it lets us really focus on the aesthetic area. And again, it attacks that area from a 90-degree angle, which allows for much easier access to those particular tricky areas. And then talking about what we use for benchmarking these machines. Um, I think there's two types of restorations, especially now with modern demands, that you really can kind of mill in your machines and know what the capabilities and the limitations of your mill are. So the first one is flexible RPD frameworks, which is a workflow that we developed. It is a challenge because it's such complex geometry, right? You have the clasps, the undercuts, the finish lines, the special posts, and then you have to have a very intimate fit with the way teeth fit into those particular sockets. And also it's a very thin material, so it needs to be structurally stable while milling out all these delicate features. It's a very challenging product to mill, uh, especially in metal, but again, as complex in flexible RPD resin. And then why do we try to develop this protocol? Well, flexible RPDs or flexis uh, uh, are facing that really big challenge of labor availability. The processing time on these cases is extremely long, upwards of 6 or 7 hours, because they require manual waxing and then they require the injection protocol. If you look at something like a Valplast, many have tried to sort of create a 3D printable material that's flexible, but it's just not there yet. And so we work with TCS to sort of like get their flexible resin, flexible pucks, and develop special protocols through a lot of R&D of milling the entire framework and milling the teeth separately and just clicking them together like Legos and saving ourselves hours and hours of post-processing time and have predictability at the same time. Why? Because it's extremely difficult for me to go and find 10 highly skilled removable technicians. It was not so easy. It was not so difficult maybe 10, 15 years ago, but it's getting extremely difficult, increasingly difficult, and we're going to talk about why. So it's all about that automation. And then the next one is direct to multi-unit, which again, direct to multi-unit is a new workflow, which we're going to go into more detail, but it requires a lot of very miniature complex geometries to be milled out just right so that you can have a zirconia restoration screwed directly to the multi-unit. And as you can see, we have a question for the poll asking you, are you currently milling direct to multi-unit abutments or screw retain zirconia restorations? I would like to know, it is a new trend that is starting to develop simply because it is much easier to produce since you don't require cementation of tie bases and you don't require having a large inventory of tie bases. So it reduces the cost of production and at the same time allows for more predictability. So you don't have to rely on potentially having a user error of how they cemented those tie bases. And the only thing you have to keep in stock as a lab are those special FDA-approved screws approved for direct to multi-unit restoration. And so because we took the tie base out of the equation, now the whole thing has to be milled out of zirconia. So that's why those complex geometries come into play. Let's see. I don't want my clicker is not very responsive today. There we go. So I keep talking about labor availability, and I like to watch a lot of documentaries about, the economy, the geopolitical stuff, and also demographic changes and how it actually everything drives economies. And it's the little things that you think that would matter. So there's a guy that I follow. He's a geopolitical analyst. His guy's name is Peter Zeihan. He works with the U.S. government and a lot of large banks and companies. And so I follow a lot of his analysis, and I see it's directly affecting our industries. So his quote is that the baby boomers are the largest generation we've ever had. And as of recent months, half of them have already retired, which means that the other half are due to retire in the next 10 to 15 years. I believe this month was the first time the baby boomer generation had peaked at 65-year retirement age. They passed that age. And so in the next 10 years, they're all going to be out of the workforce. The reason that's important is there's some of the most skilled technicians you're going to find in our industry. Some of the people that redefined our industry and that made it in such a behemoth that it is come from that generation. So there's a lot of knowledge about analog removable, crown and bridge, or orthodontics, like occlusion. A lot of that knowledge is just going to go away. And so a lot of labs are implementing different strategies to see some of those technicians work with younger technicians so they can transfer all that vast knowledge so that we can implement it, because it's really important, and utilize the new technology such as digital dentistry to kind of complete the package and get the best possible restoration out there. Every sector in the U.S. economy is affected by this, and the demographic change presents a challenge in terms of labor availability and requires us to focus on exploring every possible avenue for developing better and more reliable automation through material science, artificial intelligence, and mechanical engineering. Going back to labor availability in our industry, this is why we need a lot of automation. This is why other industries need a lot of automation. There's just not enough people to do the work. And so in our industry, faster means more product in the same amount of time, right? So production time is a direct consequence of skilled labor availability. So this is what drives a lot what's happening in the industry and why everybody's jumping on the AI and the automation and the virtual intelligence bandwagon. Direct to multi-unit challenge. So here I'm just gonna show. So this is a geometry of a multi-unit titanium base sitting in let's say a single screw retained crown or a part of a zirconia bridge. And so the titanium base is pre-machined part, right? It's pre-sandblasted on the outside, but inside is pre-machined in a way that the top portion is very short, the part that receives the screw, and the interface side is conical in shape, obviously. And so these are relatively easy pieces to machine. But now, after it's machined, you have to cement it. So you have to make sure that there's no contamination there. You have to make sure that the ceramist or whoever's doing it is feeling good that day, that they haven't, put one of the tie bases in crooked, that there's small gaps, there's small variations there in milling. And so now that we're getting rid of the tie base, which is we're going directly to multi-unit with zirconia, now the challenge is we have to remill that entire interface as part of zirconia. So now instead of having that small seat for the screw, now we have to deal with the entire length of a screw retain case and attack a screw channel from both sides. So this is where that 21 millimeter bullnose burst comes into play. But more importantly, I say, dot the I's and cross the T's. The T cutter is a really important tool. As you can see here where I have it marked in blue arrows, the desk screws sit at a sort of like a ledge, which is 90-degree cut on the inside. It's extremely difficult to get that particular angle coming from the occlusal direction, so you actually have to attack it from the interface side. So what you do is you have this T cutter that can just pass enough through the screw channel, and then the T cutter goes back and forth and clears that 90-degree angle that you actually need. So this is what, you ask a lot of labs, they would say, oh yeah, we do direct to multi-unit, it fits fine. In reality, what they're not seeing is hidden right inside of zirconia. So this would be the correct fit, right? Where all the threads are engaged and you clear that area. But what a lot of labs don't see, and it would be difficult for me to see, is that if you don't mill out that particular area, you're going to end up with something like that. You get partial thread engagement, which means now we're out of spec with the multi-unit abutment. Now we're out of spec with the actual screw, which means the specifications that those are designed for to take on occlusal forces and lateral forces. Now we're just hoping that that basically the case is going to survive and everything's going to be just fine. So this is really important when you mill these cases to know that you actually mill that whole area out correctly so that you know that you're going to have full thread engagement. You'll get all threads engaged in that case. So the software allows us to see that. Other nesting software might allow you to go through with the nesting process, and they won't give you any warning if that particular area has been milled out or not. But in HyperDent, it actually gives us the warning. It allows us to see that and give us a warning telling us, hey, there's a limitation here. We don't think this particular crucial area is going to be milled out. So let's change a few things about this before we actually send it to the mill so we don't waste your time. This is really important for us and gives us the right tools so we can kind of nip it in the bud before we spend 2 hours milling something, taking it out and realizing that it wasn't good. So even though this trend is becoming very popular, it's really crucial for you to get the right componentry, hardware and software to make sure that it actually can produce the part that you need. Here is just an example of HyperDent as we're nesting RPD flexible framework. It's very easy to use software, very streamlined, takes full advantage of the hardware that you have, which we're going to go over. But you see here, when we nest things, talk about complex geometries, you can see that we have those special stubs that we create for the teeth. We have the clasp, we have the undercuts, and very thin framework. The benefit, obviously, with a C-clamp, as I'm sure all of you know, is that we can get that design to the edge of the ring, save ourselves some milling time, and attack it from a 90-degree angle. And here you can see how we can do those user-defined areas where we want to make sure that we have that sort of like HD milling quality to ensure that those particular areas, which are the functional part areas, which are going to be receiving those teeth, they need to be milled at a high quality. They need to click like Legos because we need a finishing technician to take the two pieces, put them together, adhere them together, and polish them, and just get them out of the facility and make sure that this case lasts for a long time. Here, you can see an example of teeth. Obviously, you see how we can get it all the way to the edge. We, for removable cases, usually mill our teeth. We haven't really found a printable resin yet that we can sort of say reliably is good enough, although we're testing a lot of 3D printed resins here. We just need to give them a little more time before we can say that this is a really good, long-lasting material. And here you can see sort of like taking this was a combo case denture facing a flexible denture, full denture facing a flexible denture, where you can see how we take these pieces and kind of like put them together, all the componentry out of one PMMA disc, and the rest of the componentry coming out of the flexible puck. So what drives all this? Again, going back to hardware and software, you can use AMD or NVIDIA GPU. Obviously, don't try to. My advice would be not to try to save money on computer components. Computers are what drives production today. So I would invest in like a really high-end computer. Sometimes if the manufacturer can sell it to you, either have it built by someone or have it custom configured. The HyperDent software takes advantage of AMD or Intel CPUs on a high end when it does all the calculation. So really important to speed up that post-processing time. And when it comes to just manipulating your object in 3D, that's what it utilizes the GPU, which is the video card. So I would strongly support anyone's decision to really pay attention to their hardware and what you're using to do all the production, because you'll be surprised how much time you can save by upgrading to the right hardware. You can save hours and hours of production sometimes, and we do that for other labs as well when they ask us about advice. So that unique RPD workflow was really important for us because it really, like I said, allowed us to benchmark how good this machine is. The design was really made with really tight parameters. There was really not a lot of wiggle room. And so we inspect multiple things when it comes to these flexible RPDs. We want to make sure that the finish line of the clasp is being good. We want to make sure that the stubs that support the teeth have the correct geometry so that the tooth can actually correctly fit in there. And then we obviously have to fit it on the model to make sure that all the undercuts have been milled out correctly so that the function of the clasp hasn't been changed in any way. So we would get, it's actually brilliant of how much this has changed our workflow. Our removable techs love it. So they would get two pieces like this. They have a tooth with a pre-milled intaglio side. They get the framework and it drops right in with any modification. So what we're looking for is that natural emergence from the tissue. And I keep using the word Lego because this is what you're really looking for. You want that Lego experience that the components just click together. And that gives you a lot of confidence that the production process hasn't been altered by any sort of factors in terms of inaccuracy, variation, design, or anything like that. So this is what they get, and then they use special adhesive from TCS to sort of like complete the denture. Let me just go ahead and click here just to zoom in. Yeah, so you can see what sort of like level of detail we're looking for there. Now remember, this is a flexible material. It's a plastic-like or acrylic-like material, if you want to call it that. That spindle speed that you're milling at needs to be just right so that you get all of the features that you need and not burn out the material or under mill it. So there's a lot of play that there's a lot of parameters that we needed to tweak to make sure that this came out just right, and the XTCera and HyperDent were perfect for us to do that. And then here, since this was a combo case, here on the left, you can see it was a full upper denture and a lower RPD. And what we're looking for is, obviously, because everybody's skeptical about new digital dentures, they're not as good as acrylic dentures. We want to get that natural emergence profile and that seamless fit between the base and the tooth. And so this is a Lucito 199. Obviously, this is the number one denture material that we use for full dentures because it allows the clinician to reline it. Like we said, there's a lot of materials out there that are coming out that might look interesting, but you need to think practicality. This denture is going to be good for at least 5 years. That's how insurance reimbursements work. And so you need to make sure it's serviceable during those 5 years. So Lucitone allows us to do that. It's been very consistent material, tried and true. I think one of the longest in the market. So we really like it. And so we sometimes use corded teeth, but most of the time, everybody just wants milled teeth because some of the higher end PMMA stuff can be really aesthetic and strong at the same time. And then here, let's just change this. Here you can sort of get the close-up of what that case was like. So the lower, obviously, flexible RPD and the upper Lucitone denture. And here, oh yeah, this is a good shot. So here I wanted to show sort of like the type of finish that we're looking at those flexible frameworks. So if you have accuracy, you're going to get that intimate fit between the lingual stabilization clasp and the actual 3D model. If there's any sort of inaccuracies, it's very obvious with flexible dentures or any sort of removable work. If something doesn't fit, it's going to lift the whole frame up. So you're going to see those gaps. So we're happy to report that we don't see that. So this is what sort of allowed us, give us the confidence that we can produce this product and scale it and stand behind it. And then talking about Lucitone, it's just an example of how we sprue the actual base. This is from a carbon 3D printer, but the process is very similar to any other 3D printer. So we want to make sure that you support all the areas going all the way up to interdental papilla, not going into the sockets, and at about a 70-degree angle with horizontal bars connecting the palatal side so that there's no sort of like structural deviation for the denture as it gets printed at a 70-degree angle. So the higher you go in z-axis, which is the height, the more deviation and distortion you can find with a lot of 3D printers. It's always safer to print flatter, but then you have to cover the entire palette or maybe some other areas with sprues, and there's a lot of cleanup. So we try to avoid that. So this is the only cleanup that we actually need. So taking it out of the printer, again, Legos, we want that Lego fit that just kind of like goes right in. And as you can see here, what I wanted to show is that the cleanup is very minimal because those are the leftover sprues. Taking them out of the printer, we remove them while the material is still soft, it hasn't been light cured. So it's a very quick process using a silicone wheel to just kind of clean that up, cut off those palatal supports, and you're basically ready to go to put adhesive in, click the teeth in, and put it in a light curing unit, which is a desk light curing unit. And basically the product is ready to go. So that allows us to produce a case like this completely digitally from beginning to the end. It basically changed our entire removable department, which right now the removable is experiencing that biggest change because of the demographic changes that we're seeing. So we have a extremely limited number of removable techs we can find. So we try to get them whenever we can, and we try to take all the knowledge and implement it so we can streamline this removable protocol since we see a giant demand for it. It hasn't gone, the demand hasn't gone, but the talent has. So we try to implement it in our workflows as much as possible. So this is just one example of what we do every day. And yeah, so hopefully it was helpful for you today to kind of realize what we change here at Aurora, why we change certain things, and sort of what are the sort of things we're looking for when it comes to upgrading our equipment. I'm curious to know if you guys currently have a need for upgrading, and what are the sort of factors that you take into account when choosing the right piece of equipment for yourselves. And this is just one example of what we were looking for and where we found success. And hopefully it was eye-opening enough for you that it will give you maybe a better way of making that decision in the future. So thank you.
Thank you, Milos. And if you have any questions, please type them in at the Q&A, but we're going to go over the polls right now. So it seems that 40% of our attendees are looking for a new mill. So that was the first poll. And as far as the second poll, if you feel a strong, robust mill is needed to grow your business and your offerings, 100%
Yeah.
that it is needed. So I wanted to let you hear that and see what your thoughts were on that.
Yeah, well, this was sort of our thinking too. When people talk about comparing the mills, you got to compare apples to apples, right? So taking a Roland, for example, I actually love the Roland mill. It's just that each piece of technology has to belong in a certain category and has to apply to certain needs. So as our needs have changed and the demands have changed, we had to sort of streamline our production and go more robust and go more reliable. And this was our deciding factor. So if you're a small lab that doesn't have those needs, you can take what I like to call consumer grade mills, but it's an understatement. But you can go with a more standardized mill out there. It's just that for someone like us, this was the right direction to go. So I do understand the need of many of you to have a more robust solution. So yeah, that doesn't surprise me.
The next two questions, kind of funny, Milos, had the same percentage of yes and no. So direct, are you milling direct to multi-unit? And are you milling removables? 38% of our attendees said yes, they are, and 63% said no, they aren't. So I found that to be funny that the numbers were the same. How do you feel about that?
So you saying that the 30, how many percent are milling
38%.
direct to multi-unit, right?
And also removables.
And also removables.
Yeah.
Interesting.
Yeah.
Well, I actually thought that number was going to be lower. The 38% is actually a pretty decent number considering where we are with technology. And so that gives me hope. It's also good that because more and more people are doing it, that the companies are gonna be creating better technologies, better machines and software to sort of compensate for the needs of the market. So it's just sort of like going to drive the market even more, which is good. And then removable, you say, how many are milling removable? I'm sorry.
38% are.
38% are milling removable. That
Mhm.
number needs to be higher for everyone. And hopefully I was able to explain why, because there's such a big demand for removable. And remember, if you're a lab that does have a lot of skilled removable technicians, that number will go down in the next 10 years for sure, especially you have like high industry veterans working for you. So if I were you, I would have them work side by side with your CAD designers and teach them everything they know and pay them to teach them everything they know, so that you would have this really robust workflows of designers who understand both analog and digital worlds. Definitely streamlining and digitizing your removable department is I think really important.
Awesome. So again, any questions, you could just type them into the bottom, but Milos, I feel like you answered so many questions.
I hope
Just,
so.
yeah, definitely. You will be getting to see Milos at Lab Day West if you're joining us there. He is going to be one of our presenters in our education center, where we'll be in Salon 7 on May 17th. So please take a look. If you go to Lab Day West, we have some great education and you get to meet Milos up close and personal, which will be great. Just want to let you know about what's coming up on Zon Academy. We have on May 8th a lab's journey with the auto finish, which is an automated finishing and polishing machine that will also be at Lab Day West as well. So you could take a look at that machinery up close again and join us on 5/8 if you want to learn about a little bit of automation and what that can do for your business, especially on the polishing side. Again, we will be having Nemotech software and treatment planning with Daniel Alter, and that'll be on May 22nd. So right now registration is open for those two courses. So please take advantage and join us here again on Zon Academy. We'll be coming to a city near you. We just came back from Nashville with everything you want to know about 3D printing dentures, and it was a great show. And, you know, we met a lot of great people, and all of our attendees got to learn from industry experts, but also each other. So please join us if you can in Salt Lake City. We're going to be there on May 3rd. And on June 14th, we'll be at Columbus, Ohio. And that show will be a little bit different. We're going to be unlocking digital designs and new digital workflows with an innovations showcase. So that'll be a really cool show to join us. And again, that's on June 14th in Columbus, Ohio. We really look forward to seeing all of our customers live, and we really have a good time. Check your inboxes because there will be a special thank you from me in your inbox, and that will contain special promotions just for this particular webinar, and they're only good for about 2 weeks. So if you're interested in taking advantage of any of those, contact your Zon representative. If you're looking for an XTCera, or if you want to incorporate HyperDent into your laboratory, again, contact your Zon representative. They'll help you along with that, and also get you in touch with Henry Schein Financial Services if you need it. We have great different options for you, like Route 66. That's no interest for 6 months, no payments for 6 months, and the next 6 months you get for $99 a month. So you can really get these pieces of equipment, whatever it is that you may need, up and working for you with very little out of pocket in the beginning, so you can get all of those pain points out, really get to know this piece of equipment and get it working for you again before you have to be paying for anything. So I just want to thank you all for joining us here, especially Milos. We really, really appreciate you and appreciate your knowledge and your expertise that you share with all of our attendees and our customers. So thank you so much. And we
Thank
look
you.
forward to seeing everybody back here next week. Have a great one, everyone.
All
Thank you
right.
again.
Bye-bye.